Okay, Assalamualaikum warahmatullahi wabarakatuh. We're going to continue with the three-phase full wave 6-pass uncontrolled rectifier with the case of source inductance, the existing of source inductance and highly inductive load. So what is that? So this is the source. You look at that. This is source inductance. They may come from the inductance of the cable, and also the transformer winding is always there in the system in practical. So we must address the existing of this source inductance in the case of we have a highly inductive load. So we're going to look at what does it affect the system in terms of the operations, the output voltage, waveforms, and so on and so forth. So the currents through the circuits. Okay, so to understand the circuit operations, let's consider that we are focusing on the transfer of current from D1 to D3, right at this particular intersection between red and yellow phase current voltage. Okay, so without the source inductance here, the transfer of current from D1, right? The transfer of current from D1 to D3 happens instantaneously, isn't it? So we have this D1 current will jump from IDC, which is the current at the output. It will jump from IDC to 0 instantaneously with a sharp change there. And also, if you consider the yellow phase current, it will also jump from 0 to IDC, instantaneously without the source inductance. And we have a nice, we talk about the output voltage, we're going to see a nice 6-pass output voltage for 6-pass rectifier, isn't it? Right, but now, due to the existing of the source inductance, because of that source inductance here, okay, we're going to look at, and we see that the current doesn't change from, the switch from D1 to D3 instantaneously. However, the current through D1 will reduce with a certain rate from IDC to 0, and we also see that the current through yellow phase will rise from 0 to IDC with a certain rate. There is an overlap of current during this transition of current. So we have the overlap of currents, and this is known as the overlapping period from 0 to U. Here you can have a U, sometimes known as a U. And during this time also, we see that the diode 2 also operates, right? So we have D1, D3, as well as for the bottom group, we have D2 operates during that transitions. Okay, so now because of that overlap, we see that we observe also the output voltage now no longer has this 6-pass rectifier, at 6-pass waveform. There is a missing area here. If you can draw that, this is the missing area from the usual 6-pass output voltage waveform with a 6-pass output voltage waveform. So there is a missing area here. So we need to address what happens during that overlapping period. And there are three analyses. We're going to analyze the circuit, and we're going to have 3 objectives that we need to achieve, which is the first one will be the instantaneous equation. We're going to obtain the instantaneous equation for the output voltage during the overlap period, which is that voltage. We're going to look at the instantaneous equation of that voltage. And then we move to the overlap angle. We're going to get the equation for overlap angle. And finally, we're going to look at the average of the output voltage. Right? The equation for the output voltage. Right. So let's start with how to get the instantaneous equation for output voltage during the overlap, V out T. So to do that, we need to consider this overlapping equivalent circuit during the overlapping period. But we see that the D1 is on, D3 is on, as well as D2 is on at the bottom group, for the bottom group. So here we have VR, okay, and then we have VY here, and we have VB here, and then we have this source inductance here for red phase, as well as yellow and the blue phase, right? And the diode here will appear as a short circuit, D3 also short circuit, and D2 also short circuit. So in the equivalent circuit here, it will appear as a short circuit with a current IR flow through it. And for yellow phase, for D3, there's also short circuit, and we have a current of IY flow through it. And here we have this D2 short circuit. We can have IDC that flow back to the ID2, or we can have the summation of IR plus IY that flow through the output, which is equals to IDC that flow through the ID2. So this equivalent circuit actually represent the whole rectifier here during the overlapping periods. Okay, so having that equivalent circuit, then we can resolve for two equations. One to describe the loop from there into the red phase loop, and then goes through there, through the load, and come back to VB. And we're going to consider that loop. Hence, it will give you this equation here, which is V out T equals to V red minus VB minus LS DIR over DT plus, minus LS DIR plus IY over DT. So that gives you the first equation here. And next is we look at the second equation. And now we consider from that point the yellow phase, okay, yellow phase through the LS DIY. Then come back to here, go to the load again through the blue phase and come back to that neutral point, right? So with that, we have the second equations, whereby we have V out equal to VY minus VB minus LS DIY over DT minus LS DIR plus D over DT. So we have two equations here. Add them together, add both equations, that give you 2V0, okay, 2V0 plus VRB plus VYB minus LS DIR over DT plus DIY over DT minus 2LS DIR plus IY over DT. We know that hence we know that the IR plus IY equals to IDC. This current actually similar to the current here, similar to this current, right? So that's why IR plus IY equals to IDC. So if you differentiate a constant, then you get a 0. So we have DIR plus DT plus DIY dt equals to DIDC equals to 0. Okay, so now since IDC is constant, thus the overlap, so you substitute that DIDC over dt into these equations, then you will get the output voltage, the V out here actually equals to VRB plus VYBT over 2. This is actually the average. The voltage here, V out, is actually the average between the two line-to-line voltage. We have a line-to-line voltage here. It's actually, there's a line-to-line voltage across that and across that. And we look closely, the V out during this overlapping period is actually in the middle between the two line-to-line voltage. And that is already proven by these equations, whereby V out during that overlap equals to VRB, which is the line-to-line voltage between red and blue, plus V yellow blue divided by 2. So that the voltage equations to describe the instantaneous voltage during that overlap period. Okay, so we are done with that. Now we're going to look at the overlap angle. What is the equation to describe the overlap angle during that overlap? So to look into that analysis, we now change to that equivalent circuit. We just focus on this particular loop. Okay, we only consider this loop going up here through yellow, then come back to yellow voltage again. So that on the loop. So this is what we're going to focus, right? That loop, right? So we have VR, Vy, and 2LS. And now in this analysis, you need to set an IU current, the current that flows during that overlap. So this is known as the, consider that. So we assign IU, and that the direction of IU must follow the current that flows after the overlapping period. So if you consider D1 and D3, the current that will flow after the overlapping period is actually through the yellow phase. Yellow phase. So you must follow the yellow current directions, not following the red current. So if you follow the red phase current, you will be clockwise. But now, because after the overlapping period, the yellow current will flow through the circuit. So we have IU set to follow the direction of IU. Okay, so having that equivalent circuits, then you solve for KVL around the loop. So we have, if we follow we can follow this route if you like, or that route. Okay, so that path. So we have minus Vy plus Ls diu over dt plus Ls diu over dt plus Vr, and that gives you these equations, right? Vy minus Vr equals to Ls diu over dt equals to 2 omega Ls diu over d omega t, or d theta, right? So you place the dt to be d theta. So now then you cross multiply the d theta or d omega t here, cross multiply it. So you have at the left hand side, you have 0 to u. You integrate from 0 to u, and the voltage of Vy minus Vr over 2 equals to omega Ls, and you integrate the current IU, which is from 0. You must understand how you get this 0. So you actually refer to that particular current. Okay? So you have a limit of 0, lower limit is 0, the upper limit is IDC, because you start with 0 and you end up with the IDC. So that is your integral 0 to IDC of I diu equals to omega Ls IDC. So you solve this, you get omega Ls IDC. So this also the line to line voltage. And if you turn it into the equation, instantaneous equation, then it becomes V peak line to line. So it becomes V peak line to line sine theta d theta. And then you have 0 to u on the left hand side, and the right hand side you have 0 to IDC 2 omega ls diu. Okay, I think we have solved this before. Right, so you cross multiply the right hand side and you solve that, then that gives you the equation of v peak line to line minus cos u. Solve that, and finally you find out that the angle, the equations to describe the overlap angle is actually equals to cos u, or you can take the u equals to inverse cos of 1 minus 2 omega s idc over v peak line to line. So you must have everything correct. It is a peak of the line to line voltage, so you have to consider that cos u equals to 1 minus 2 omega s idc. So that gives you the equation for u. And finally, we're going to look at the average. What will be the average voltage equations for the output voltage? Okay, so to obtain that, to determine the average equations of the output voltage, let's consider this. All right, so this is the second. So we need to consider this area. So this is the missing area that we talked about just now. So during commutation interval, the voltage drop across the line is equal to the shaded area. So there is actually a voltage drop across the line inductance, and this is represented by that area here. So we need to find what is the average of the voltage drop here, so that we can just simply subtract the average equation that we had before without the source inductance, and you just subtract that with this missing area, the average of this voltage drop. So to be able to do that, we just simply look at the equations here. So we know that the V out here is actually in the middle between the two line to line voltage. So how to get the area under the curve? You integrate VYB minus VB. So this is, let me zoom it. So this is your VRB, and this is VYB. Right? So what the equation does here is actually you integrate the whole, you're going to get this area. Okay, and then actually you divide by 2, because we know that the output voltage here is actually run in the middle between the two line to line voltage. So it's to get the this first area, we just divide the whole area by 2. So this is what this equation does, and that gives you 0 to u. Again, Vy minus Vr, you can cancel that Vb, so it just left Vy minus Vr over 2. And then if you equate that equation 2 with equation 1, you will get that area equals to omega ls IDC, and therefore the average voltage drop becomes that area divided by pi over 3, which is 60 degrees. So omega ls IDC, so each pulse consists of 60 degrees, so that's why you divide by pi over 3. And finally, the average voltage can be described by this equation, which is 3V peak line to line over pi. As I mentioned earlier, this is the voltage equation without the source inductance. Okay, no LS. This is without the source inductance, and then you subtract with the missing area here. So that gives you the average load voltage VDC. Right. So that's why that is all about the analysis to determine analysis of the circuits with the existing of the source inductance. Here we can see that the output voltage now is different, and also the current, if you focus on the red phase current, is no longer a quasi square waveform. There is a slight change here. If there's a quasi square waveform, there's a sharp change here, then quasi square waveform, but now it is slightly different waveforms here due to the existing of the source inductance. And it is also to address the distortion that's been created by this source inductance. Right? So if you look at this particular point of common coupling, as I mentioned earlier in the video, that the source inductance may come from the cabling. It is behind the wall. If you talk about those wall sockets, that source inductance is actually behind it. And from that point of common coupling, you're going to have a load 1 as your rectifier, and probably load 2 can be other load, which is your PC, your laptop. So because of that rectifier and the source inductance operations, now we see that the VPCC, the voltage at the point of common coupling here, is actually being distorted. It's no longer, this is the voltage from that point to the neutral point, and these 2 points. So similar to the red phase voltage, I mean here we have the voltage just before the source inductance, which is actually from the TMB. So we have a nice sinusoidal voltage, but due to that rectifier, the voltage across that point of common coupling, at the point of common coupling, has been distorted. So you can see that this is a distorted waveform here, and we know that with that distorted waveform, there will be a harmonics. There will be a certain harmonics exist in the output voltage, and therefore other equipments will receive distorted voltage supply if they are connected at this point, and that load also will receive will also deal with the harmonics of the supply voltage. Okay, so that's all about this three-phase full wave bridge with a source inductance and highly inductive load condition. Thank you.